This is Team 3377, North Carolina School of Science and Mathematics from Durham, North Carolina. So the first question in the Moody's Mega Math Challenge is, what is your name?
I'm Erwin Lee.
I'm Zach Paluzzi.
I'm Annie Lee.
I'm Stephen Liao.
I'm Jennifer Wu.
Welcome. You may begin.
Hello everyone. We are Team 3377 from the North Carolina School of Science and Mathematics, and this is our solution. So the lunchtime problem arises from a large number of students being unsatisfied with the current meal plan. And primarily, many students are leaving school lunches being unappeased and relatively hungry. In addition, since schools put so much emphasis on the nutritional value of the lunches, they do not fully consider the taste of the meals. And this continues to create an increasingly large number of students who leave the school lunches being hungry. Coupled with the rising cost of produce, it makes it exceptionally hard for schools to create an adequate meal plan that is both satisfying, nutritional, and filling for the students. So our role is to devise a mathematically based model that is not only filling and nutritious, but also satisfying for the students. And in our solution, we wanted to consider, first of all, the average lunchtime caloric need for all the students. And from this, we were able to calculate the current percentage of students that are actually satisfied with the current meal plan. And then afterwards, we want to check for the funding possibilities to see if there's any financial issues with any new or potential meal plans in the future. Using this, we wanted to check for the students' food preferences as well, using a survey in order to maintain overall acceptance of food for the students.
In the first part of this problem, we set out to create a model that would allow us to calculate the amount of calories a student needs at lunch based on their individualized and personalized attributes. There currently exist many models that allow an individual to calculate how many calories they need over the course of an entire day. However, there's no currently accepted models that are widely used to calculate how many calories you need at a specific meal. So to approach this problem, we made a set of key assumptions. And the first of these assumptions really gave us a way to approach this problem. And it states that the amount of calories required at lunch is equal to the number of calories burned since the last meal. So for example, if a student burns 500 calories in the time period between breakfast and lunch, they're going to need to eat 500 calories to make up this deficit at lunch. And this makes logical sense because, for example, if a student exercises a lot in this time period, they're going to need to eat more calories at lunch to make up for the greater number of calories that they might have burned. For this assumption to hold true, the next two assumptions also need to be made. And the first of this says that an individual at the previous meal will eat until they're full. This means that there will not be a caloric deficit at the previous meal going into this time period. And also that the number of calories burned is equal to the number of calories consumed. And this isn't strictly true. For example, for a normal, healthy, growing child, they'll need some calories to keep their rate of body mass increasing. However, this is relatively small, so we did not consider this for simplicity. So to calculate how many calories a student burns over a specific time period, we created a rate equation, which you can see in this diagram here. And this diagram shows the rate of calories burned as a function of time over the course of the entire day. So as you can see, while they're sleeping, their rate of calorie burn is relatively low and increases as they wake up, and specifically for exercise periods. And to construct this graph, which is unique for each student, we used a set of survey questions, as you can see here. These questions involve things like, what time do you normally wake up and go to sleep? What are your eating habits, activity habits, and what is your weight? The weight allows us to scale this function up and down, as research has shown that rate of calories burned is directly proportional to body weight. And to evaluate our function and our model, we wanted to test it with some currently accepted models, specifically the Institute of Medicine Estimated Energy Requirement model. And so to compare this, which is a day-long model, we simply integrate this function over the course of the entire day to find how many calories a student needs over the day and compare it to the results of this model. As you can see the results in the chart here. For 4 random students from a distribution we have, you see that the percent error between these two models is relatively low, especially for models that are so diverse. And back to the problem at hand, which is how many calories does a student need to eat specifically at lunch. We simply integrate this function from breakfast to lunch in the case that they eat breakfast. However, research has shown that up to 2/3 of students do not actually eat breakfast before school, so we need to consider this case also. And in this case, we have to integrate all the way from dinner to lunch, which, as you can imagine, incorporates a much higher caloric need at lunch.
So after we created a function to model the amount of calories each individual student would burn, we wanted to test for the sensitivity of our model. And so we changed the various parameters of our model, the weight, the workout time, and the sleep time, by a small 10%, and we wanted to see how much it varied. And as we found, weight, workout time, and sleep time varied as expected. However, our model is incredibly sensitive to whether or not the students would eat breakfast.
So in part 2, our goal is to determine the proportion of students that are satisfied by the current calorie content of lunches provided by schools. And this is about 850 calories as determined by federal guidelines. So we make 2 key assumptions that must be noted before we can proceed. The first is that we assume students fully consume the entire 850 calories. Secondly, students are satisfied if this 850 calories is within 15% of their calculated need. This 15% is determined by the Institute of Medicine, where they state that if the 15% variance is sufficient in maintaining the student's body weight. So you may be thinking, well, in part 1, we need personal attributes of the students, such as their weight, when they eat, whether or not they eat breakfast, how often they work out, and the rigor of their physical activities. So how were we able to evaluate our model, and where were we getting these numbers from? Well, our distribution of lunchtime caloric needs is based on data from the National Youth Physical Activity and Nutrition Study. This study surveyed approximately 12,000 students, where they answered questions such as their weight, how often they ate breakfast, how often they worked out, and the other answers to our survey questions. In addition to this, we found a distribution of sleep times for high school students from a paper written by Charlene Kolinkowski and others. So in this table that you can see right now is a sample of 4 different students and how we calculated what their lunchtime caloric need is. From this, we were able to generate graphs. So this first graph is from the set of the data set and of students that do not eat breakfast. So as you can see, many of them need about 1,400 calories, which is much greater than the 850 calories plus or minus 15%, as this creates a range of 723 calories to 978 calories. So in this green box are all the students that need more than 978 calories. So there's no way that their caloric need is being satisfied. However, we also need to note that there are some students whose caloric lunchtime need is less than 723. So by fully consuming the 850 calories, they're overeating, and therefore they are neither satisfied. So this creates a kind of Goldilocks scenario, where some students do not get enough calories, some students get too many calories, and then there's this optimal range where they get just the right amount. And so what we find is that the students that fall within this 723 to 978 calorie range, only 0.07% of breakfast skippers are satisfied. In this second distribution graph are the students that do eat breakfast. And again, if you take into account the students that need more than 978 calories and the students that need less than 723, we'll find that 68% of them are currently satisfied. And so in this distribution graph are the 2 previous graphs overlaid upon each other. And you'll see that currently 37% of students are satisfied by the 850 calorie meal. And so what we want to do is we want to optimize this 15% variance range in order to maximize the percentage of students that are satisfied. And what we find is that the optimal calorie content is 1,049 calories, and this will satisfy approximately half of the student population.
In part 3 of our model, we apply what we've learned in parts 1 and 2, and we seek to create a meal plan that schools can serve to their students. In creating the meal plan, we have 3 main criteria. First, the meal plan should fall within the school's budget, which means they cannot spend more than $6 on a student's food over the entire week. Second, the meal plan must meet the student's nutritional needs. And finally, we seek to optimize student acceptance of the food, meaning that we give preference to the food that students prefer to eat. So what do we mean by nutritional needs? In our model, we define nutritional needs into 2 components. First, in order to meet the student's nutritional needs, the school meals must be served according to USDA MyPlate recommendations. This means that the portions of the meal should be 30% vegetable, 30% grains, 20% fruit, 20% protein, and 1 serving of dairy. The second component of the nutritional needs standard is that the number of calories in the meal must be such that it satisfies the largest possible percentage of the student body. This optimum caloric content we found to be 1,050 calories roughly in part 2 of our model, but this will vary by school. And one important note is that we assume that fractional servings are possible. So the first step in creating part 3 of our model was giving out a survey to all the students in the school. The survey would list every possible meal item that the school could serve, and this could be tailored based on what's locally available. The survey would ask 1 question for each meal item. Would you eat this meal item if it were served? And based on this, schools could gain data about student acceptance of foods. Secondly, we would put all the data into a Python program that we built, and the Python program would run through every possible meal combination, where each meal combination is 1 dairy, 1 vegetable, 1 grain, 1 fruit, and 1 protein. And for these meal combinations, we would first divide them into the proportions set by the MyPlate recommendations, and then we would calculate the number of servings required to meet the optimum caloric content. If the cost of this number of servings is more than $6, we throw out this combination. For those that remain, we rank them by student acceptance, and that is based on the data we received from the survey. So to provide a proof of concept of our model, we created a sample data set. Above are the top 3 meal plans, and below are the bottom 3. Now, these aren't exactly the meal plans that we would recommend for schools, since this is just sample data, but this provides a proof of concept of our model. And finally, one important note is that most schools are able to serve more than 1 food in each food group. So a school may serve 2 vegetables on the same day. So that would even more increase the number of students that can be satisfied by the school lunches.
So going over the overall strength of our model, we were able to calculate exactly the lunchtime caloric need of a student based off of the personalized attributes, while many models and calculators out there will give you the total caloric need over the day, but not during lunch. And so we also were able to generate an algorithm that gave schools the best combination of foods to serve during their meals based off of a survey that we give to students. So this will increase the student involvement in the meal planning process, which will also likely increase their appreciation of what they're being served and will have them more inclined to eat more of the food that they get as well. And so in our model, we use many simple and easy, intuitive to understand relationships to create our algorithms. So this will help us explain our model much more easily to the school administrators who will actually be using our model to implement the results that we find. So some weaknesses mostly lie in our assumptions that we make. So first of all, we assume that the person's metabolic rate is constant during any given activity, which may not always be true. And we also assume that an individual will be full after every single meal, but if they don't get enough time to eat, this condition is not satisfied. And we also assume that fractional servings are possible for the foods we serve, but when we get down to specific decimal numbers, it's hard to provide that exact amount to the students. And as our model currently is, we can't handle foods that fall into multiple categories, such as maybe a pizza, which would contain grains, dairy, and vegetables. But with a few modifications, we predict that our model will be able to handle these foods as well. So in conclusion, what we have done here is we created a model that would give you an individual's lunchtime caloric needs based off of personalized inputs. And from that, we noticed that one of the biggest factors affecting their need is whether or not they ate breakfast. So based off of this result, schools can have an additional option to maybe implement breakfast for their students to be able to satisfy more of their students at lunch and throughout the day. And with current lunch servings of 850 calories, only about 37% of students are satisfied. But if we increase the calorie content of these lunches to approximately 1,050, we'll be able to satisfy around half of our student body population. And lastly, what we've done is also create an algorithm to help schools plan their meals that they'll serve their students and increase satisfaction, taste, and as well as make their meal plans affordable to their students. And so thank you for your time and listening to us. Do you have any questions?
Thank you. I have a question for you. I was first going to ask you about the first question. I really liked especially that the diagram. I think it was, it was nice simplicity. It was very easy to understand, and I thought that there was lots of value in providing that to the reader and also the watcher, right, of the presentation. But one of my questions was your primary assumption was based on this idea of what I would really consider like a look-back perspective, right? And why did you choose to go in that way as opposed to a look-forward method where you eat in order to prepare for that next activity?
So we actually started solving this problem with a look-forward method. We had all the algorithms written, and then we were working with it, and we realized that it really didn't make sense because if before lunch you have a PA class or some sort of sports activity, you're gonna get really hungry for lunch. I mean, that's just how our body works. And we kind of thought about it as like a bucket filled with water, and at each meal you fill this bucket up to the top, and that's like your calorie bucket. And as you exercise or whatever, this bucket slowly drains out at the rate at which you burn calories. And so it makes sense to think about it as a before method because the calories are burning and then you fill it up at that meal.
Thanks.
Since the competition, have you had a chance to try out your algorithm, say on your own school's sort of data? And if so, are there any changes that you would consider making?
So we have not been able to get data from our school just because it's been kind of a quick turnaround. But in the future, if our school would like us to analyze some of their data, we'd be very happy to help out.
Are there any changes you would make in general to your model at this point?
As we mentioned, one of the significant weaknesses in actually implementing our model is that we can't handle foods that have more than one group. For example, like she said, pizza, which has meats, grains, dairies. But we think some very simple changes to our Python program could allow this to be included, and then our algorithm could actually be used in a school.
I have a question. What were your thoughts when you concluded that only 37.9% of the students are satisfied? Were you surprised, shocked? What did you think?
I'm sorry, could you repeat the question?
Yeah, you found that only 37.9% of students were satisfied. What did you think when you discovered that? Were you surprised or shocked or?
Yeah, we were pretty shocked that only maybe like a third of the students are satisfied with like current meals because they have to like go through the rest of the school being hungry, and really like being hungry doesn't help you focus in class. And
that's very good. One other thing, it was impressive. You said you used a survey, the adolescent and school health National Youth Physical Activity survey. That was very good. You also used something that we did something with sleep times, but that was from a different source, right?
yes.
Could you tell us how you incorporated those? How did you put that data together?
Okay, so what we did is we took the distribution of sleep times, and we basically took that distribution and generated random sleep times from that distribution, with the right probability, and we just added that to the data set as another column. So it's a slightly non-ideal method because, for example, a student that wakes up really late might not have as much morning activity as the sample might have suggested. But we think that's a relatively small weakness, and it really allowed us to analyze our model in a really effective way. So we think the slight weakness is worth the benefit that we gain from that approach.
What led you to construct your own model rather than using one of the many models that I'm sure you are available?
So are you talking about part one where we're trying to find how many calories at lunch? So the current models that we found at least are really for how many calories should you eat over the course of the entire day. And we didn't find any models that were widely accepted and good at calculating how many calories you need at a specific meal. So our model is able to do that, and we could use our model for any meal. We just analyzed lunch here because that was the problem. But we think our model is unique relative to current widely accepted models in that we can do specific meals.